Hi guys, I'm Mikael Alamar, and this is Lab 4 Oscillations. In this lab, we checked out the motion of a mass connected to a spring that was also moving in an arc. Thus, the purpose of this lab was, given the properties of the spring mass system, to investigate its motion while the mass oscillates in an arc. For the modeling, we put our experimental data video into a tracker to collect the data and put it on a graph. We tracked the motion in the software, and then we dove into the physics and solved for the equations and parameters for this experiment. And then we put it into GlowScript, which is a computational model meant to interpolate the predicted motion of the mass. The reason we used GlowScript was to create a perfect condition graph of motion, which resulted in a similar appearance to the graphical data and an energy that remained zero, meaning the energy principle was upheld. Here's a look at our observed motion from the tracker. The given values were found in the pre-lecture videos, and each has an equation. For example, delta t was essential because it's the frames per second of the video. The mass of the object was weighed. The ks was found through the spring equation, and the same with the kn. We also found these motion graphs on the bottom, which I'll talk about in a second. We're going to take a look at the periods of those graphs for the what if question at the very end. So this was our tracker data, and here's our code overview for part one. Hold on. Here's our code overview for part one. A couple things to note here. This was where we inserted our initial properties, most of which were covered in the last slide, such as the mass, the initial velocity of the ball, and the explained values in the previous slide. At the bottom, the purpose of this lab was to look at the energies and energy principle. So here we have the equations for K, potential energy of the spring, and the potential energy of gravity, which are taken from the textbook. In the second part of our code overview, we have initial energies, which was just naming variables, and then we have net force calculations. Here we have our position and spring update formulas, and finally we have some energy changes, which basically say each frame this is what's going to change, meaning current values minus initial, because initial is updated within the while loop. So that was the code that was outputted. This is our result of our code. We have the motion graph on the left here, and then on the right we have the motion our code predicted versus the experimental XY position graphs. And on the top is the most important graph, which is our energy graph. The most important line is this one. Is the delta E, which is 0, the orange line. That's important because that's an important thing to note. And then moving on to the conclusion. Number one, the sources of the error. I mentioned in introduction that we purposely use GlowScript for a perfect prediction model. However, this can be taken with a grain of salt because it assumes there were no forces at all due to the surroundings, which is just ignoring its surroundings. Even though it's an isolated system, there are still interactions with the surroundings, like everything that is attracted to each other through the universal law of gravitation. And even though those effects are small, they can be significant. Also, we have tracking error since we tracked this in tracker and the video was tough to track, so getting the center of the ball each time perfectly was not possible, which introduced some error within the XY graphs. However, we can draw some other conclusions from these graphs. Number one, was the energy principle satisfied? Looking back at the orange line, since the delta E system was constant, the energy principle is satisfied. Ignoring sources of error for a second, no external forces were present in this lab based on this result. At the bottom, we looked at the periods of the X and Y graphs, and in these estimations, we found slightly different periods. I took a look at the 3 periods for each, and for the 3 periods of the X graph, it was 5.02 seconds, while 3 periods of the Y was 4.56. These are different. Rearranging the K equation, we have 4 pi squared times ball mass over period squared gives us the Ks value, and for X this was 5.69, whereas for Y this was 6.87. So different values, which was interesting to learn. And yeah, so there were a lot of takeaways there. And that's it.